2.3 is titled Derivative Function, kids, and our essential question is how do you sketch the derivative of a function and what does it tell us? Now guys, the sketching part will be something that's pretty new for you, but I think you'll catch on to this. But I want to make some connections to the idea of shortcuts of derivatives, whether it's a constant function, linear function, or some kind of a polynomial function. But in order to sketch these derivatives, we first of all want to make sure that we can do that, sketch the graph of a derivative. But we're also going to use what? To construct slopes near a point. That'll be pretty easy. This is my favorite right here. This makes me happy. Derivative shortcuts. Lake would probably say, see a cut? Take cut, right? Okay. We're going to find shortcuts to derivatives. You know that big long f of x plus h minus f of x all over h stuff? You start plugging that in and they get kind of lengthy. Okay. We're going to be shortcuts that you'll be able to just look at it and know instead of having to write all that out now. Okay. Happy with that? All right. And then also want to identify where graphs are either or. Guys, when a graph is increasing, what type of slope do you have? Positive slope, and decreasing is going to have a negative slope. So let's talk here quickly, vocab-wise. You guys, we've spent the good part of the last couple sections talking about the derivative. Specifically, it's a slope at a what? Point. And we've looked at this formula a lot. We've said, you know what? We can define a derivative at a point as the limit of h approaching 0 of f of x plus h minus f of x all over what, kids? So today we want to start looking at some shortcuts. And these next three vocab terms are really going to define some shortcuts for us. So here's the deal, kids. This says the derivative of a constant. For instance, some function f of x equals some constant k. Like maybe f of x equals, I don't know, 6. Guys, if I said graph f of x equals 6 or y equals 6, what kind of graph would you get? A straight line. What kind of straight line? Horizontal. Well, guys, you tell me about a slope of a horizontal line. What's the slope of any horizontal line? So if f of x equals 6 is nothing more than a horizontal line, what's that mean about the derivative anywhere? In fact, I don't care where you put a horizontal line, f prime of x will always equal what? So if I ever have a function that's what kind of a graph? Or if I have a constant, some number, the derivative of any constant is always what? The derivative of a constant is, I'm just going to write 0. Right here, okay? Derivative of a constant is 0. Okay. Well, what about a linear function? What's true about a line with a slope? Does that slope ever change on like y equals mx plus b? It's constant, isn't it? If f of x is ever in linear form, like mx plus b, guys, I'm just going to tell you right there, the slope is constant. Which of these variables up here represents the slope? M. F prime of x has to equal m right here. So if I ever say, ooh, the derivative of a linear function, you could say is the slope of the what? So as an example, f of x, you ready for this? Equals 6x minus 3. What's the derivative anywhere? It's just 6 because the slope's going to be 6 everywhere on that line, isn't it? Right? So f prime of x in this example would equal 6. Now, what's really new today, and here it really is, kids, the derivative of a power function. I'm going to write it like this, if you have some function. Now keep in mind, this is kind of a power function right here, isn't it? This is like x to what power? Okay, let me show you some things here. If f of x is equal to some power function, say maybe a x to the, I'm going to use n up here, sometimes I use p. The thing you need to understand is that a and n, there's some number. Okay? A and n are some number. The derivative of this function then becomes the following. take this exponent and you pull it out to the front. So it becomes n times your leading coefficient of a, and n times x. And then what you do with your power is you bring it down by 1. So if you listen to what I said here, guys, move your power out front, simplify, and bring your power that you had originally down by 1. Now think about this one here, kids. This is 6x to really what power? What's 1 times 6 out front? And then x to the first would become x to the what? But that variable to the 0 power is really what value? 1. So 6 times 1 gives you that slope of 6 there. Okay? Let's do an example here. Even want to guess what the derivative for any x value is going to be for the function 7x to the 4th?
I take the 4 up front, which would make it 28.
28?
And then to the third power.
So it'd be 28x to the third power. Very good. Okay? 28x to the third power. If you see a power up there, all you're doing is you're pulling that 4 out front. So essentially you have 4 times what out front now? 4 times 7, right?
Could you keep doing this for like ever? Taking the derivative?
As long as it's a power function. Yep. And we're going to look at some examples here real quickly. Okay? We're going to look at some examples here real quickly. In fact, we're going to jump to the last page. We're going to jump around in this. We're going to do this a little differently, out of order, and that's fine. Okay? Well, let's just see if we can find some derivatives. Jump to the last page. Kids, says, use shortcuts to evaluate derivatives. First thing they want you to do is to evaluate the derivatives at what? 6. Now I could make you do the f of 6.0001 minus f of 6 and do that all over 0.0001. You want to do that? I could make you find the derivative algebraically, f of x plus h minus f of x all over h, and then plug in 6. You want to do that? Or should we take some shortcuts? Oh, come on, what should we do? Take some shortcuts. Hell yeah. Oh, wait, I'm recording that. Heck. Take some shortcuts. What's the derivative of f of x equals 7, kids?
7.
What?
0.
It's a constant, right? It's a horizontal line, be 0. So if I want to know the derivative at 6, f prime of 6, what's it going to be, guys? 0. Okay, at the point 6 comma 7, that slope to that point is still going to be 0 because it's a horizontal line. Okay? How about the next one? F of x equals 6x plus 9. What's going to be your general derivative for any x value here by shortcut? Oh, this is fun now. Who said not fun?
I said not far enough.
Oh, not far enough. Oh, I thought you said not fun, but this is so much fun. Guys, what's f prime of 6 going to equal then? Because the slope everywhere on a linear function is the same, right? I don't care if we were evaluating 12, 42. F prime of 6 is what value? 6. Now this is where shortcuts get really cool. Because we want the derivative or the slope at what point, kids? X equal what? Okay, let's start using power rule. X cubed is my function. What's my general derivative, kids, by power rule? So bring the 3 down. So we can say the slope at any point on a function x cubed can be found by 3x squared. But what x value are we concerned with now? Guys, take a look at this function right here. When I had a derivative right here, was there any x value left in the derivative over here, or was it just a value? Same thing here, it was just a value. But now we've got stuff in terms of what here? So if I want to know the slope at 6, I say, okay, well what the heck is f prime of 6? I don't know. Plug it in. Now kids, my north of Highway 3 math skills tell me that 6 squared times 3 is 108. You like that? So the derivative, f prime of 6 equals 108. Kids, hear me out on this. If I can use shortcuts to find derivatives. Can I use those derivatives to find the slope for any x value then after that? Just by plugging it in. Once you found your derivative by shortcut, plug in your x value, and that'll tell you your slope. Okay? Now, what happens when we start combining things here, kids? How many parts exist to this polynomial function up here? How many terms are in that?
I have a guess. F prime of x of.
Well, like, this is kind of an answer to the question I think you were trying to ask earlier. What's your guess on the derivative?
Well, the first stage or the second stage?
There's only going to be one stage to it.
Well, f of prime x is equal to 12x minus 6. That's my guess.
Close. You're kind of on the right track. Here's the deal. Let's see if we can't miss. How many terms do we have in this right here? 1. And then here we said the slope is 6. But guys, isn't that 9 like a constant right here in the second one? And the derivative of this is just going to be what? Derivative of a constant we know is what?
0.
So this was like 6 plus 0, which was just got you what? Okay, so you treat each term like its own individual, and you just differentiate all of them. Okay, so what's the derivative of the 2x cubed term going to be?
It's going to be
6x to the,
second.
let's move. How about the minus 6x squared?
X.
Now again, this 8x is like 8x to the first.
I have plus 6.
Ooh, not plus 6, plus
Well, it'll be
plus 8 now. Now keep in mind here, guys, this 2 is a constant whose derivative would be what? And maybe another way to think about it is like saying this 2 is out here with how many x's? 0. What is a 0 times 2 going to get you? 0 out front times x to the negative 1. I don't care what x to the negative 1 is. I know that 0 times x to the negative 1 is still going to be what again? Well, 0. Okay? Now, is there enough information up here to find the derivative at x equals 6? You bet there is, because what are we going to plug into your derivative now? 6 times 6 squared is what it becomes. Minus 12 times 6. And then plus 8. I have to think on this. 6 squared and 6 is 216. 12 and 6 is 72. So 216 minus 72 is 144. Plus 8 more. 144 plus 8 is what? $152. Okay. Is that slope pretty steep or not very steep? Pretty steep, okay? I say, Lake, we're running hills tonight. The slope's 152. Lake's going to look at me and be like, all right, bring it on. All right, so we're going to use this idea of shortcuts to derivatives when we get back from lunch here to write a shortcut for a tangent line approximation. So